Laszlo Babai, and he's at the University of Chicago. He gave a talk on this last week. The talk is now available online, which you can watch if you're interested. And he's going to have a write-up hopefully sometime soon. The actual proof of this is very interesting because it goes through group theory. If you think of reasoning about computations on a graph, they form a group. And it turns out that what you need to do in order to get this improvement is to think more about the group structure of this problem than the graph structure of this problem. Which is, people have known this for a while, but they hadn't quite figured out how to do it. And at a high level, the proof is divide and conquer. Take the graph, divide it into small enough pieces, do brute force into small pieces, and then figure out your answer. Now, how you do the divide and conquer, why you can break them into small pieces, and how this all works, that's where all the group theory comes in. You have a question?
Okay, is that the worst case bound for making up with?
Yes.
So, but that's not...
For any graph, you can do this.
Okay, but that's not enough to prove it's not or does that by itself prove it's not an NP-complete?
No.
Okay.
No, because maybe all NP-complete problems can be solved. Maybe P is equal to NP. We don't know anything about it. This doesn't tell us anything about P versus NP. It just means that this problem is unlikely to be NP-complete. Because if this problem were NP-complete and had that running time, that means all problems in NP had that running time. That means NP was not that much worse than P. And we generally are suspicious of such claims. We don't think that's likely to be true, but you can see how cautious I'm getting now, because we don't know. It could be true. If P is equal to NP, this is all true. Right? We just don't know. It just seems like given current evidence, it seems unlikely. In other words, if this was true, and it's for NP complete, lots of even weirder things would happen that we think are even less likely. So complexity theory is a chain of assumptions and things like, if this assumption holds, this will happen. If this assumption holds, this will happen. And there are weaker and weaker, or stronger and stronger and more bizarre assumptions. And things that might happen. One of those bizarre things would happen if this were actually NP complete. So we think not, but we don't know. Anyway, are we good? Okay. So with that brief interlude over, let me actually get on to the business of the lecture today. And it's all very exciting if you care about these things and you realize that there's a problem that someone's been working on off and on for 32 years and it's finally cracked. It's kind of cool. That level of persistence you need to think about that. So, one of the things that has changed, and I've harped on this, off and on in this class, right? And as we're nearing the end, I want to harp on this a little bit more. One of the things that has changed in the way we think about algorithm design, of course, has been dealing with large data. I think this goes without saying. And we've seen the reason for that. The reason for that is that things you thought you could do that were considered efficient are no longer efficient. So we used to think, and if you went through undergrad or if you grew up at a certain time and you were told what is an efficient algorithm. So you were always told, okay, if you're a complexity theorist, efficient means polynomial time. And of course this is kind of a lie because if I give you this algorithm that runs in n to the 107 time, you are not about to go run out and implement it. You're going to look at me like I'm crazy. So it's not as true that polynomial time means practically efficient. What we meant was that there seemed to be this huge gap. There were problems that were solvable in some polynomial, and there seem to be problems that are kind of hard to do so, right? Your SAT, your vertex cover, and I put dots there because we don't know the truth here, but they seem to be much harder. It doesn't matter what polynomial you have, they seem to be hard to solve. And so polynomial time seemed like a nice, convenient mathematical definition of what is considered tractable, because these other problems are just way harder than that. What's also true, I can't say this is a formal theorem, but it's actually true, is that if someone actually did come up with an algorithm that ran into the 107 time, and this has happened before, time and again what has happened is that, someone said, wait a second, I can do n to the 106. Oh wait, I can do n to the 95. Oh wait, I can do n to the 37. And eventually, they end up with something which actually might be practical for small. I'm not saying this is always going to be true, but this is invariably what has happened. That the minute someone shows, yes, it's in P, there's a whole engine that comes on and gets it down to something reasonable. So it's not a bad notion of efficiency. But of course, in the era of large data, even an algorithm that runs n squared is bad. If you have a gigabyte-sized graph, you have a graph with 1 billion nodes in it, let's say a Facebook graph or even a web graph or WebGraph will be much bigger, but anyway. You can't run anything that runs in n squared time. It will just not finish. It will take forever to do anything at all. N squared does not work. N squared might be great for aligning protein sequences. It's not going to be good for analyzing the WebGraph. So you say, okay, fine, I can sort stuff. I can do things in disk. I can do efficient sorting. And then you quickly find, well, n log n is also bad for large data. You can't even sort anymore. And when you can no longer sort, a lot of things you take for granted are now gone. You have to think very differently. We're going to see a lecture next week by one of the TAs. He's going to talk about streaming algorithms as one way to think about how to design algorithms when you don't have the luxury of even sorting the data. You just get one shot of it. And so many things have come up to change how we think about algorithm design in the light of things like n log n not being efficient, and even n being sort of only tolerable. Depends on the right kind of n. Some linear time algorithms are okay, some are not. And so a lot of the research that has happened in the last 20 years in algorithms has been to move away from the traditional things, things like flows, dynamic programming, and all things like that, and to move towards methods that are randomized, as we've seen, are approximate, as we've seen, and somehow can tame this complexity of the data, that don't do much of the actual data, and can somehow shrink it down to something more manageable. Right? And so that's what I want to talk about today. Sort of give you an introduction to the way people have been thinking about how to shrink data down so you can do something with it. And roughly speaking, what you want is the following. So I'll define something which I'll call a core set. And I'm going to define this informally, because when you define it formally, there are different ways of defining it. So I want to do so I have an input. So I have some input, let's call it P. I want to compute quickly S, which is a subset of P, then the size of P. Sorry?
Make S the null set.
I'm not done yet.
Okay.
And whatever you wanted to compute on P, you can compute on S. And that takes care of your null set.
Actually, I think it does.
Depending on F. So this is so the idea is very natural, right? Okay, I have this large data set, I want to compress it, right? It's compression. I want to compress it down to size, not to store it, because compressed data you can store, but you can't do much with it till you uncompress it. I want to compress it and work on the compressed representation. Okay, so that whatever I wanted to do with the original data set, I can do on my compressed representation. Whatever kind of queries I want to ask on the original data set, I can compress it. And the reason for defining it this way, in this informal fashion, is to emphasize that for different Fs, you might have different S's. I'm not telling you there's a universal small size set that will work for any problem you might have in your data. You have to know ahead of time what kind of problems I want to solve, what kind of questions I want to ask. And then you have some hope of computing this. Because if you can do this, and S is very small, so let's say you had some algorithm that ran on P and took time. So there was let's say computing F takes G of P time, okay? So running your algorithm on P will take G of P time. Running your algorithm on S instead would take, I don't know, let's say let's say P. Let's say you can compute S in a linear scan over P plus G of S time. And the hope is that if G of P is very big, if it's n squared for example, then you've reduced that dependence on P to linear, or a good linear, and your dependence on S is quadratic, but S is very small. So you're okay with it. For example, if S is less than square root of the size of P, and G was quadratic, you have a linear time algorithm. Yeah?
Just wondering, when you said n squared is bad for large data, with RSA encryption, if somebody figured out how to factor in n squared time, would RSA still be a danger?
Yeah, because the things you're factoring are these 1024-bit numbers. They're not large data, they're tiny.
Okay.
If your key was a billion bits long, then yes, n squared would really help you. But keys aren't a billion bits long. They're 256 bits or 512 bits or whatever. So that if you can run it time quadratic in that length, that's easy. You're easily willing to pay that much time to crack something. So that's not a big data problem. So is this sort of goal clear? That what you want to do is compress so you can operate on the compressed representation. And the win would be that your running time would be a lot less. And of course you'd pay some price here, right? I'm not going to get the exact answer. But now you can talk about approximations, you can talk about trade-offs, you can talk about what S is going to look like as a function of the error you want, and all kinds of other things that we're used to saying. But that's the goal, to do a compressed representation. Right? And you've already seen examples of this. So let me give an example where there's a very natural compressed representation. And maybe you haven't thought about it that way, but it nevertheless is one. So here's my problem. You're given a graph. Okay? And my query is a pair A comma B. And the question is, are they connected? Okay? Now, of course, you can do connectivity checks on the graph. It takes linear time and the size of the graph. So you can run this in time which is basically this, the worst case could be the square of the number of verticals. So let's say V is equal to n. So this is O of n squared, worst case. Can we come up with a core set, a small compressed representation of the graph that allows us to answer these queries easily? Yeah?
So if we compute a core set, we should also be able to compute it efficiently, right?
Yes, but remember, you might compute the core set only once, but you might ask queries many, many times. So in that kind of situation, even if your core set construction is a little expensive, it's a one-time thing. So let's ignore. So in other words, let's ignore that issue for now. It's an important issue, but given the fact that you might do the queries many, many times, it's okay to ignore that for now. Another question?
Oh, I was going to try to answer.
Okay, so let's hold on a second. Let's think about this for a second. So what do? I want you to build some compressed representation of the graph so you can answer these queries, and you want to do this per query in time less than n squared. What could you do? This is actually the solution to this is something that you would have covered in undergrad algebra. It wasn't called a core set, but it is one. So the problem is, of course, all these edges, right? You don't want that many edges. Is there some version of the graph that has many fewer edges on which you can still answer these questions correctly? Yeah?
We are not looking for a direct line. We are just looking for a path between A to B.
Yes. Or even a yes/no answer. Are they connected?
MSG,
Even without the end.
yeah.
You don't need the end.
Yeah.
Suppose you build a spanning tree on the graph. So my core set. A tree on n nodes has how many edges? Any tree on n nodes has how many edges? N minus 1. Can I answer connectivity queries? Yes, of course. I just run the same algorithm as I did before. But now it's on a much smaller graph. So my running time, if my original running time was n squared, I'm paying, n log n, which is the time it takes to compute the spanning tree, or rather m log n, which is not great, but it's a one-time cost, plus g of s. No, sorry. Yeah. Sorry. Hold on. Let me write this carefully. I'm not being careful. number of edges, so which is equal to, and this is the key, that for all your queries, this is what you're going to pay. You're not going to pay n squared. So it's a very simple example, almost a trivial example of a core set. If you talk to researchers who work with core sets, they would not consider this a core set really. But it's really the same idea. A compressed form of the graph on which you can answer correctly all the queries you want to ask. So in other words, this is possible. It is possible to build these compressed forms. But for each problem, you have to think carefully. For connectivity, it turns out you need a spanning tree. Maybe for a different problem, you need something else. And so what I'm going to show you is some examples of how you can build these things and how effective they can be for your problem. Yes?
Instead of spanning tree, can you also do strongly connected components?
Or connected components.
Yeah.
Yes, but how will you represent the connected components? As sets. And often you will represent them as, so I should call this a spanning forest, maybe. Right? So you'll have one set of connected components here, one here, and you might store them like this, just for convenience. And you can do a lot better than this, by the way, right? You can build unifying data structures, you can do all kinds of funky things. The point is to answer that query about connectivity, you don't need the whole graph. You just need enough information to maintain connectivity. And so this is just a proof of concept that you can do that, and you can do a lot better. Right? If we build a unifying data structure, you can answer these queries in almost constant time.
So I thought the idea with the connected components was that you could view all the nodes of a connected component as just a single node.
Yes, you can. But then you have to know for a given node which components it's in. So you got to keep track of that information somewhere.
Oh, I see.
Yeah, so that's effectively like making a tree. So you can build core sets. So let's look at some more examples of how to build core sets for problems. And the goal again is always to reduce the data size. So I'm going to look at two examples. One is a sort of a more geometric example, and you can take this as a kind of a small teaser for the course next semester, if any of you are interested in taking that. Another example comes from another domain that's been very active in the last 5-10 years of building core sets for NP-hard problems. I'll show you one example. All right. So the problem I want to talk about is the following. So this is a problem, and you can think of these points in the plane. I have a collection of points in the plane somewhere. Okay. So this is a set P. Diameter of P equals to the distance between x, y. So it's the distance between the furthest pair in the set. So in this case, I'm not entirely sure, but I suspect the distance from here to here might be a diameter pair. Okay. So I give you a point set, and I want you to compute this diameter. Because it's a very easy problem to solve. Just run the definition. It'll take n squared time. So there's an easy n squared solution. Can I do better? If I'm willing to be approximate. So the usual sets, I will have some parameter epsilon, and I'm willing to give some answer. So can I give some output, some such that since we're maximizing, you want to get close enough. So this is one way you can think about trying to approximate. So I want to give a number that it's larger than the actual value times some small discounting factor. Again, it should be more than 0.9 times the right answer, or 0.95 or 0.9, whatever. Okay, we've seen this in approximation. Can we do this and not pay n squared? Is the question. Can we do this in particular time that depends linearly on n, but might depend in some other complicated way on epsilon? waiting. What happens next?
Oh, that's what I was saying. You just randomly sample to a distance, and then you keep doing that, say like 10 times n times, or
Yep.
we can analyze that, but, and then you find the longest distance.
Sure, and that's a reasonable strategy. I don't know if that'll work. When I hear that strategy though, one thing that worries me is that it's possible that the diameter pair is just one pair in your set. So if your set is kind of very long and skinny, almost a straight line, there are 2 points that give you the diameter, everything else doesn't. What's worse is that, so let's think of this example. So let's say I have an example here where I have 1 point here, 1 point here, and a cloud of points in the middle here. What is the probability that I pick the correct pair, or even anything close to the correct pair, right? With, yeah, so in this case, picking the correct pair is 1 over n squared probability. Picking something that's within a factor 2 of the correct answer is 1 over n. Is actually pretty high, because if I have to pick one of these, so it's 1 over n. I have to pick one of these two and then anything in the middle. And that'll give me a 1 over n probability of getting a factor 2 approximation maybe. But other than that, I'm dead. If I pick any pair in the middle here, I'm going to get a tiny answer. So I'm not saying that your sampling idea is wrong, but when you think about things like that, here are the kinds of examples you should consider to say, okay, what could go wrong? Because sampling assumes that you have enough witnesses for what you're looking for. And diameter is one of those problems where you might have only one witness.
So I guess it works if you know that your samples are sort of evenly distributed.
Maybe.
But-
Yeah, it might work then. Any
Yeah.
other question?
So, is our answer delta tilde upper bound?
Is it upper bounded? Well, I mean, you're presumably going to give an actual pair. So it's upper bounded by delta itself. That's it.
Yeah, I figured it was probably upper bounded by it.
Right, because I guess the intent is I would like to give you an actual pair of points. Here's a candidate for the net. Yes?
Could we try a greedy strategy, like take the leftmost x and the rightmost x and then combine the corresponding points and do the distance and see if it's, or try something like that?
Good, very good. So what happens if we do that? Let's think. Again, let's think, what can go wrong? You have to be very pessimistic in these things. So what could go wrong? So you take the leftmost and rightmost. Here's an example. You're going to be off by a factor of square root 2. Well, you know, in this case you won't. If you actually take the leftmost and rightmost, you'll work fine. Because it'll work out this way. Pardon me?
Vertical.
Well, then you could take the y. You want something where either way doesn't work. So for example, you could take something that looks like this. If you take a V shape, your leftmost, rightmost will break. Your topmost, bottommost will may or may not work. It might, but it might not. In other words, these are things you should be trying to do with that strategy. Come up with examples and see what you can do with it. Right? Yes?
We define leftmost, rightmost, uppermost, bottommost with like higher dimensions.
You define left and right as left 1, right 1, left 2, right 2, left 3, right 3, left 4, right 4, left 5, right. In other words, for each dimension, you look at the min and the max. Right, so there's a left and right along this dimension, there's a left and right along this dimension, there's a left and right along this dimension, and I could go into 4 dimensions, but I need something more stronger than coffee for that. So yes.
What about a line of best fit?
A line of best fit.
Could that somehow help?
Okay, suppose my data set looked like this. Will that help? Maybe it will, maybe it won't, I don't know. And you can say, oh, well, in that case we use the sampling strategy. Maybe. In other words, these are all good ideas. What you have to do is test and see how they will work with specific cases. And they might, I don't know. But again, in all of this, you remember, the goal is to be arbitrarily close. The problem with some of these strategies is that they'll get you up to a factor of square root 2 because of diagonals versus straight lines. It's hard to see how to get beyond that, unless you're a bit more ahead.
You said that our approximation would identify 2 points, but I don't see how we can identify 2 points and be within epsilon. Are we really having the game of identify 2 points that are within epsilon of the true, or is it really identify a distance that's within that?
Well, the algorithm I have in mind will give you 2 points. They could be the exact answer, right?
is in the case that you gave before where you have a cloud in the middle and then the 2 points on the end, your algorithm would give you those 2 points on the end?
Yep.
Okay.
You would. Yeah.
So what if you break it apart into a tree? Because that takes n time, like a case
What's a
of
tree? I have a bunch of points. What's a tree?
It's just a partitioning of space, so like a quad tree, for example.
Okay, so you build a quad tree into data?
Yeah.
Okay, good. So you have a bunch of points. So what do I do now?
So you build a quad tree.
So quad tree. So I'm building a uniform grid.
Yes.
So this is a grid. Okay. Yeah.
That's what you start with.
Pardon me?
Yeah, that's what you start with, and then for each point in there, you make a little smaller box.
Sure, sure. So I build the whole quad tree. Fine.
Okay.
Then what?
So that takes linear time.
Yeah.
Worst case.
Actually, it doesn't, but okay, we'll assume it does for now.
Okay.
If you use a compressed quad tree and you're a little smart about how you do it, you can get it. But the naive quad tree does not run linear time.
Okay.
It depends on the interpoint distance. But anyway, yeah.
But yeah, so now that you have that, I mean that sort of gives you a bounding box, but
Yes.
it's more specific because it's like curved on the edges. So you might be able to use that information.
You might.
Like it's
And-
just another representation.
Well, one thing that's interesting about the grid approach is that somehow it's trying to group things into clumps. If we're trying to reduce data size, we need to group things together somehow. Right? And in that previous example, right, a natural reaction would be for you to say, well, this is silly. Why am I wasting all this time with these points? They're so close to each other. They're not going to give me the answer. I can probably group them into one thing without paying too much error. Because whatever distance I'm measuring between them, if I pretend they're all just 1 point, I mean, how much penalty am I going to pay by doing that? Right? So if you have points that are in clumps, I should be able to group them together in some way. And so that clumping idea and the grid idea, they're all sort of beginning to sort of show the signs of a strategy here. Yeah?
What if we did something like k-means with k equals 1, right? So you start
What
with
means?
so you start with like 1 point, and then you compute the distance to all the other points.
Yeah.
And then you can just like move a circle into the middle of that point.
Yeah.
Move a circle, move a circle, until you sort of get to like some center, or some various value of center. And then the radius of that circle times 2 is your diameter.
So you'll get a factor 2 from that.
Same.
You'll get a factor 2 result from that. You will. And that will work. In other words, okay, so let me give you the strategy. So the strategy is the following. So let me make a new here. Okay, so strategy 1. Pick any point and find its furthest neighbor. Okay? So let's say I have some point P, and let's find its furthest neighbor Q, and let's say R is equal to the distance from P to Q. Okay? So here's a claim we can make. Okay. Why? Well, take this point P, draw a circle around it, just as you said. Oh boy. Okay. Here it goes. I hate drawing circles. Have you ever seen YouTube videos of the World Circle Drawing Championships? I'm not making this up. You never seen this? It's really cool. There are World Circle Drawing Championships. So these people stand on the boards like this, and they literally do this. They take their chalk and they kind of wind up. They wind up, they go, and you get this perfect circle, which I cannot do here because I don't have enough room for it. But it's really cool. You should go look it up on YouTube. Yes, for everything there's a competition and it's on YouTube. That's the lesson. So take this point P, and there's some point Q on its boundary, because that's how we define Q. This distance is R. Let's look at the actual diameter pair. We don't know where it is, but it has to be inside this circle. You see why? Because Q was the furthest point from P in the set. So every other point has to be inside that set. So the actual pair, let's say it's X here and I don't know, Y here, has to be in the set. And now you can see just visually that this distance between X and Y can be no more than 2R. because it can be no more than the diameter of the circle, but the diameter of the circle is too long. Okay? So we already have an example of getting a factor 2. If we put epsilon equal to half, we have a solution right here. Take a point, take its furthest neighbor, return that pair. That's within a factor 2. Done. What can we do better? Yep.
Maybe could we just use the easy algorithm but stop early?
The easy algorithm.
Or the easy solution, I mean.
What's the brute force?
Yeah.
What do you mean stop early?
Like, rather than completing it to the end, just depending on the value of epsilon. Like,
But how do you know when to stop? Maybe the last pair you're going to evaluate is the one that was going to give you the right answer. Again, think of that example of 2 points in that clump in the middle.
okay.
You don't know the order. Yeah?
So what is something similar to the circle is, what if we take the average point of all the points
Yeah.
and then sort of like draw a line or something to divide the two, to divide it into two sets, and then find the point in each set that is farthest away from that line,
Yeah.
and then find the distance between those 2 points.
Yeah. This could work. And in fact, this is in one way is the precursor of what I'm going to describe just now. So hold that thought. So what this gives us is a crude approximation to the diameter. And this R has a name, by the way, in the lore on approximations that we've been discussing. What do you call R? You want to find delta. You have this R which you can compute. What is R? We have a name for it in approximations land. I heard something here. Someone said something? Yes? I heard the right answer. Say it. It's a lower bound. R is the lower bound in delta, right? It's more than delta over 2. And it's not going to be more than delta. So it's somewhere below, hovering below it. This is a good thing. We know lower bounds are good. We just need someone to make use of them. So here's the idea. What we're going to do is, we're going to build a grid. So along the lines of what folks have been saying, right? We're going to build a grid we're going to first find the min and the max on both directions, in 2 dimensions. So that takes linear time. And then we're going to build a grid with a very carefully chosen cell size. So we build this grid. When I say build a grid, I just mean place points inside the grids. Right? So for each point, figure out which grid cell it's going to be in. And the length of this side is going to be some constant which we'll set later, times epsilon, which is the error we care about, times R, the number we just computed. So it's not going to be a grid size of 1 or 2 or 3, it's going to be based on the number we just computed in the previous step. And you'll see why in a second. Okay. How many cells will we have in our grid? If you do this now, if you build a grid with this side length, can you tell me how many cells you'll have in the grid? Well, you're like, well, I don't know. I need to figure out how big the sides are. But we know how big the sides are because I just said take the min and the max. We know the min and the max can be no more than the diameter, which is no more than 2R. Right? So the actual length of this side is going to be some constant, let's call it A times R. And this is going to be some other constant B times R. It's actually A times delta and B times delta, but because R is more than delta over 2, it's the same thing. Now tell me how many cells we're going to have. Asymptotically in terms of epsilon. Notice that R disappears. If you have each cells of size epsilon R, and you have size of your total length AR, how many cells are you going to have? You're going to have A over C epsilon cells on this side. You're going to have B over C epsilon cells on this side, and the number of grid cells right? Just multiply. Why is this important? Because now I'm going to say, take every point and replace it by the label of the grid cell it's in. So if a point is in here, it gets the label, I don't know, 0. If points is here, it gets the label 1. Points is here, it gets the label 2, and so on. And for each grid cell, I maintain a count of how many points are in that cell. So what I've gone now is by doing this trick, essentially a hashing trick, I've gone from P to a set G and counts, call them counts, where the cardinality of G is very, very small. It depends only on the error and not on the size of the input. I could have a billion points in here. I don't care. Okay? And now I treat each of my grid cells as a super point. So I can think of each grid as associated with the center of the grid cell. And I write down this canonical point as the point associated with a certain cell. So now I have a set of points of size 1 over epsilon squared, and now I want to find the diameter of this set. So I run whatever algorithm I want. You can run the dumb algorithm, you can actually be a little bit more clever in this case. But let's not be clever. Let's just run the dumb algorithm, take all possible pairs of points and measure the distance between them. All points that have non-zero count. It'll take 1 over epsilon to the 4th time, right? And you'll find the diameter pair. Now how good is this answer? That's a question you have to ask yourself. So now so what does our algorithm look like? So the algorithm says, 1, find furthest neighbor to any point P. Let distance be R. Hash points into grid with cell size. Okay. Find diameter pair in G. And of course, not all cells in G will be filled, right? Some will be empty. That's why you have to actually search over and find the pair. But you can really just go around the boundary.
I have a question. The first step in itself is
Linear time.
in number of nodes.
Yes.
If I have billion nodes.
But remember what my diameter running time was, n squared. I'm trying to I'm trying to go away from n squared. And even that billion, it's a single scan. Take the first point, just scan the rest. It's just reading the input once. It's a very nice linear. So I mean by nice linear. There could be bad linear. This is a good linear. Right? So the running time now is going to be n, as you pointed out, plus 1 over epsilon to the 4th. Because if you do this something very dumb, you just do a brute force diameter calculation on the centimeter. Versus n squared. This is the win. You've gone from n squared to n, your dependency on epsilon has gone up. That's not great, but again, there are ways to fix that. The point is that you've changed your dependence on this. Most of the work is being done here. And so now the question is, how good is this? So imagine that I output the solution from my grid. So there's one grid cell somewhere here. And there's one grid cell somewhere here. That gave me this claimed diameter pair. That means there's at least one point in there, at least one point in there. What's the worst case situation? Well, in this particular geometry, it could be that the actual point for this thing was somewhere here. And for here, the actual point was somewhere there. Right? So the true distance between these 2 points, so the true distance is really the distance between the grid cells, which I'm going to record here, plus how much? square root 2 over 2 C times epsilon times R times 2. Right? Because the diagonal is at most that much. This term here, this is a diagonal, half diagonal. And there are two of them. So in the worst case, this is what it could be. Right? They're exactly in a straight line. In general, it might even be better than that, but it could be as bad as that. But we know that R is greater than or equal to delta over 2, and it's at most delta, which is important here. It's not more than delta. So this number, right? So you can rewrite this as, so we can say that the error between your true answer right, is going to be less than or equal to which is equal to, which is less than or equal to, right? And you just set C equal to 1 over square root 2, and you get the distances at most epsilon delta. And so you get that and we're done. So by doing that first step with R, that trick, we basically made sure our grid cells were not too small and not too big. They were just the right size. And then it allowed us to do two things. It allowed us to compress down to a constant, essentially, number of points, 1 over epsilon squared. And it also made sure, by balancing it very carefully, that the error was not very large. Right? If R had been too small, you would have had too many cells, but you'd have a good accuracy answer. If R had been too big, you'd have very few cells, but your accuracy would have been lousy. This is kind of the sweet spot between these two things. Your accuracy is good, and your number of points is small. Yes?
You said earlier that you would actually return 2 points.
Yep.
So suppose that the 2 points are actually in the opposite corner closest.
Yep.
That you chose, then you would actually need a C that's 1 over 2 root 2, right? Because the 2 points you're returning are not necessarily in the centers of those boxes. In worst case.
You're actually right. In fact, the worst case is that this is the diameter pair and I'm returning something that's right here. You're right. So there'll be an actual thing there. Correct. Yeah. But yeah. Up to constant we're all friends. But no, that's absolutely correct. Because I'm just going to return an arbitrary pair of points on those two grid cells, and I'm not thinking carefully which one.
But we are returning the diameter, we are not returning the pair.
No, what I'm going to do is I'm going to take those two grid cells that gave me the right answer. By construction, those two grid cells have at least 1 point in each of them. Just return any point. Anything I want. That's why you could get different configurations. The point, I don't matter. Any point in that grid cell is a good enough representative of what I really want to have. Yeah.
So since this is big data, if the points that we were given were constantly changing, then would that factor of 2 algorithm be better?
So then you'd have to figure out how, you can't build a fixed grid then. I mean, you could, well, if the points are changing, this will not change the problem, right? Because if suppose the points are changing, what do you need to do? You need to maintain the counts of points in these grid cells. So you maintain some kind of data structure, which has counts for each of the grid cells. If you delete a point, just decrease the count. If you add a point, increase the count, and just maintain it. So that's not a problem. Yeah.
What were you saying we run the...
Sorry, before I carry on, this will break if your diameter changes.
Yeah, that's right.
And then you have to, and so there are algorithms that deal with that situation as well. They get more complicated. But in the dynamic case, when points can change, you have to rethink what you're doing here. And yes, there's work on that. Yeah.
So what were you saying that we run the brute force on the grid, and then we were saying from the grid
You get two grid cells that are the diameter of grid cells. Because see, look, what I have now is this grid structure there. I associate, you can think of a canonical point associated with each grid cell that's non-empty. So it actually doesn't look as clean as that. There'll be holes in the middle somewhere. There'll be grid cells that were empty. There were no points. So for the ones that do have points in them, among them find the furthest pair in this canonical sense. That gives me two grid cells. Then actually go look at the grid cell and give me any 2 points. It doesn't matter which two, just give me 1 point from one, 1 point from the other. They're not empty, so I can do So we've compressed the data down, we've solved the problem with compressed representation, and in fact, this representation is very flexible. You can do all kinds of things with it, not just compute diameter. You can compute minimum closing balls, you can compute extents, you can do all kinds of funky things. So it's very versatile. But the point is that you can solve your problem on the compressed representation after doing a simple linear time scan to get to it. And so that's why you have this initial term for the scan, and then the term after this one. And that's a way to compress the data and do something. That's reasonable. So you have to read the data at least once in this case, but it's not. This is an example of a core set. The grid itself, the grid with a reduced size, is an example of a core set. Technically it's a weak core set, but I don't want to get into that. It's a representation of the input that allows me to answer questions. And I can tune this. Unlike in the case of the spanning tree, there was just only one answer and we just did it. Here I can tune it. If I want to get a better accuracy answer, I tune it, so I spend more time. I build a bigger core set. Any questions? Okay, let's take a short 2-3 minute break.
And then when building the course, it will pass the data.
Yeah.
Linear technology. That's what it
Yes.
is.
Yeah. 2 scans. That's the only one.
Calculating and 1/2. So what he is doing is he is just assuming just as long as his constant C and proceed with this answer. Then you will get this thing as the answer. It was just a placeholder for 1/2. C is 1/2. Yeah.
This is okay. This is C times.
Yeah. So C is R.
R is
C is no. C is 1/2 times. Yeah, 1/2. This is C. Yeah, this is C. Because he wants to keep it arbitrary so that he can derive this formula and then substitute the value of C. So it all depends on the epsilon. No, he's just assuming some value C.
So you just assume you don't know.
Yeah, at this point they don't know, so once it's constructed, we will get this thing as epsilon at this point is a given error. The error which the user wants to. Yeah. Yeah, that is not determined. Yeah, R is also. R is also supposedly value which will determine after running the algorithm.
Right, you run it once you get that. Yeah. Then A is we got C and F on A is what? What did we get out of it?
A is the left and rightmost points. Find the leftmost point of this direction and the rightmost point in this direction.
So because when you found P, when you're looking for all the
You would know
determine the
yeah, and it all
and determine the So A is the
left. A is the leftmost. minus right mouse. I mean right mouse minus left mouse. The distance between left and right, and B is the distance between the
So there are, I know.
All right, let's continue. One of the more recent trends in algorithm design has been an old idea sort of repackaged and made much more powerful the last 5-10 years. And this goes back to a different way of thinking about cosets, not for problems where you're trying to save on n squared or n cubed for large data, but for problems where the original problem was intractable, it's NP hard. So let's go back to our favorite NP hard problem. Well, my favorite is maybe not even mine, but favorite problem is class anyway. So vertex cover, right? And so we know it's NP hard, and you can get 2 approximations or factor 2 approximations, and we don't know what else, and then it's hard to get a betas and blah blah blah. We know a bunch of things. But if someone says, "Look, I actually want to solve this problem. All these things that I cannot do are not helping me. I need to do something I can do." One way to think about the problem is to say, well, what happens if we know the value? We have some sense that we're dealing with graphs where the vertex cover is of size 3. Okay. So it's a thought experiment. Suppose I told you that, okay, I'm going to give you a graph and you want you to find vertex cover. But I will guarantee you that the vertex cover is of size 3. I just don't know what it is. Can you solve this problem in polynomial time? It's vertex cover, but I'm telling you something very interesting about it. What can you do?
Try every pair of 3 points.
Every group of 3 points, right? Try every group of 3 and check if they form a vertex cover. We know it's easy to check if something is a vertex cover. That's why it's an NP. So given a set of 3 vertices, I can check if they cover all the edges. And I can enumerate over all sets of 3. It takes me n cubed time. So suppose I have graph G, and I have a promise that the vertex cover of G is less than or equal to 3. Then I can find it in n to the 4th time. It takes me linear time to check, maybe n to the 5. So definitely n cubed times n. Right, for each possible set of 3, I just scan all the edges and make sure they're covered or not. Wait, but this is polynomial time. This is the vertex cover problem. Check if a graph is a vertex cover less than t. And I'm giving you a solution polynomial time. What's the catch?
It's not the same problem.
It's the same problem.
But you change it for that promise.
So the vertex cover problem that's NP hard is given a graph G and a parameter t, is the vertex cover less than t? Or not? If it's more, I don't care. I just want to know if it's less than t or not. Why can't I run this algorithm? It will take time n to the t times n. What's the problem? Yeah? T could be n. This running time is not polynomial in n if t is part of the input. But if I say that, look, I'm only dealing with graphs of size, with vertex covers of size 3, then 3 is not part of the input, it's a constant. And I'm allowed to spend time exponential in that number 3. Because it's not an arbitrary parameter t that could be in. In other words, if you fix a parameter for a problem and call it t, and you can get a running time that's polynomial in n and has some other function of t which could be bad, then this is called fixed parameter tractable, or FPT. Notice that this is different to what I gave you earlier. What I gave you earlier was n cubed times m. That's not what I want here. I want the terms involving n to be separate from the terms involving the parameter. And I want my dependency on n to be polynomial. That is not true in that case. because that will be n to the t times m, so it will not look like this. But if I can do this, then just like before, I have separated out where the complexity is coming from. That is not coming from the size of the input, but it's coming from the size of the output, or the value of the output we want. So if I actually had a situation where all my graphs had vertex covers that were small, I could run an algorithm like this and get the exact answer, even though the problem is NP hard in general. This doesn't work for all problems. There's a whole hierarchy of which problems can be solved in this way and which problems can't, and what hardness levels and all. But if you can find a parameter such that this is possible, then you have a big win. Because now you can take a problem that was intractable and make it tractable. And it turns out vertex cover is one of these problems. But what does that have to do with core sets? It turns out that the way you solve this problem is by finding a core set for that problem, for the graph, or for that input, which has size that relates to t, and then running your brute force algorithm on that set, just like we saw earlier. So it's a different kind of core set. Again, in the literature, if you think about core sets, you're not going to usually come across these things which are called kernels, it's a different name, but it's the same idea. Find some core that captures the thing you're looking for. Hope that core is small, and then do whatever your brute force is in the small thing, instead of having to do it in the big thing. Okay. So let me show you how you construct such a kernel or core set. So this thing is called, this is called a kernel, and the problem admits a core set, I'm going to put in quotes, called a kernel. And I should just say this is yet another overuse of the term kernel, which has many, many, many names in the literature. But that's just how it is. It's the core, the nugget, the nugget. Okay, so how do we do this? So I'm going to give you an algorithm for vertex cover that will construct a kernel from it. Okay? And I want to do this by a series of transformations of my graph. So my first rule is, take a graph G, and I want to, and a parameter T, right? And I want to check if the vertex cover is less than or equal to T or not. Okay, so this is the parameter T. So the first check is, we'll call it the D0 check. Remove right? If you have vertices of degree 0 in your graph, you don't care about them. They're not going to affect your vertex cover size. You just remove them. That gives you a new graph. You can also have a rule which says D1. If V has degree 1, right? Then G prime is equal to G minus V and all its neighbors. Well, V and its neighbor. There's only one neighbor. Right? And T prime is equal to T minus 1. So I'm saying if you have a graph G that you want to look for a vertex cover of size T in, and there's a vertex of degree 1, you can remove it, remove its neighbor, and then ask for the same problem to be solved in a graph G prime with the parameter T prime is equal to T minus 1. Why is that? Because if you have some graph, and you have a vertex of degree 1, you have to cover this edge. You have no choice. There's only one way to cover it. You choose this endpoint or this endpoint. Either way, you've reduced your vertex cover size by 1. And you just remove these two things. Right? So this transformation, taking a graph that has a vertex of degree 1 and removing it, and then transforming the parameters appropriately is a correct transformation. Whatever was true in the original graph is true here. Whatever is true here was true there. It's a reduction. Okay? Is this clear? So I'm just doing transformations on my graph. I want to make it smaller and smaller and smaller and see how small I can get it. Okay. Here's another tricky and interesting transformation. We'll call it dt. Suppose Suppose your graph has a vertex of degree more than t. What do you have to do now? What must be true? Remember, I'm looking for a vertex cover of size t. What can I be sure of now if I see this vertex? Yeah?
That vertex is either in the set or you don't have a solution.
Why?
Because if it's not in the set, then all of the other vertices that it connects to have to all be in the set.
And there are too many of them.
Then you're bigger than t.
Very good. So if you have a vertex of degree t, you have to pick it. Because if you don't pick it, then you don't have a solution. You'll go above t. So then you just say g prime is equal to g minus v, and t prime is equal to t minus 1. That's the transformation you can make. So if you keep doing these transformations, eventually all your vertices will be of degree less than t. And there'll be at least 2. So there's another rule you apply. And I'm going to call this rule, since I already have 3 rules here. The 4th rule up here. We'll call it DE. If all vertices have degree less than or equal to t, and the number of edges is more than t squared, then return no. So if all vertices of degree less than t, but e is more than t squared, then you cannot have a vertex cover of size less than or equal to t. You see why? Why is that true? So intuitively, if every vertex has degree less than or equal to t, then when you pick each vertex, there's only so many edges you can get. Right. In fact, you can just add up all the degrees of all the vertices, and so let me see how I can make this argument.
Okay. I mean, if there are t vertices and each of them is less than t, if we take all the t vertices, then we can get a maximum of t square edges. But the edges are number of edges is greater than t square.
I know, but I didn't say that there are t vertices. I said if all vertices are degrees. I could have many vertices. Yeah.
But you
Complete
cannot.
this argument by simply saying, suppose we pick the vertices that have the most degree, or in the best case, we can pull off t edges for each vertex, and we have t vertices that covers t squared edges at best.
Yeah. Ah, that's right. That's right.
So-
Okay, I think you were saying the same thing. Sorry. I was wrong. You're both saying the same correct right thing. Yes. Because you want to pick off only t. So if your vertex covers of size t, and so when you pull off t vertices, the best you can do is pull off t edges for each of the t vertices. So t vertices have total degree less than or equal to t squared. But e is greater than or equal to t squared plus 1. So t vertices cannot cover all edges. Okay? And these 4 observations together give you a coset. Because what do? Just keep running the rules over and over again. If you see a degree of a vertex, remove it. If you see a degree 1 vertex, remove it. If you see a degree vertex greater than vertex of degree more than t, keep it, and then continue on what you have left. Keep doing this over and over again. Either you stop at this situation where you have less than all vertices of degree less than t, so you can't make any further moves, but e is more than t squared, in which case you know your graph does not have it. Or you end up with a graph that has all vertices of degree less than t and e is less than or equal to t squared. So apply these rules. Till you stop. And if you stop without saying no, you have a graph with less than or equal to t squared edges. How many vertices do you have? Could you have many, many vertices? Could you have n vertices in this graph? No, because every vertex in this graph has degree at least 2. Because if not, you could have applied this rule, one of the first 2 rules earlier. So t squared edges and all vertices have degree greater than or equal to 2. Since you can now add up the degrees of all the vertices, the total degree is at least 2 times the number of vertices. Therefore, the number of edges is at least the number of vertices. Therefore, you can have at most t squared vertices. So therefore, the number of vertices is less than or equal to t squared. So we now have a graph which has t squared vertices and t squared edges that has the same vertex cover as my original graph by these transformations. We have produced a kernel. So now if we wanted to solve the vertex cover problem, we have an algorithm that runs like this. It says, step 1, compute kernel. This might take n squared time, I think, or some polynomial. And now 2, run brute force on kernel, which takes time 2 to the t squared maybe. So our overall running time is poly in n times 2 to the t squared. This is my first part, this is my second part, this is fpt. So in other words, by computing the core set for vertex cover, I can solve the vertex cover problem in time that only depends polynomial on the input, but might depend exponentially on the parameter. And if my parameter is small, then this is a good thing. If it's like 3 or 4 or 5, then I can actually solve this problem. And so there's a large body of work for a large number of NP-hard problems. So you can say, look, yes, they're NP-hard, but there's this parameter, which in this case is the actual value of the solution. In other cases, some auxiliary value. I can get my algorithm to run in time that is bad in the parameter, but is good in n. Just like in the previous case, we had an example that was bad in the parameter 1 over epsilon, but good in n. And again, this makes sense if you expect the parameter to not be very big. In particular, not to be growing. So this is another example of a core set, another way of dealing with sort of scale issues. In this case, it's more of a time scale issue, but it also relates to the size because it gets even worse as your input gets bigger. Yes?
Is this only worthwhile if the graph is larger than some threshold?
Or if the parameter is small enough. Both things, right? Because you're comparing this against 2 to the n. So it depends on which one wins. So either way. But there's a surprising amount of, there's some beautiful structure coming out now where you can say, oh, for this particular graph problem, there's this nice core structure that's very small that tells you whether the graph has that property or not. And this is the example of that. And there are many, many more examples of these things. If you look at the last 5 years or so, there's been a ton of work on how to do this for arbitrary problems, for classes of problems. Also, impossibility results when you cannot do this for a problem. There's a whole sort of hierarchy that you can study, which is very interesting. And again, the motivation is this idea of a core set. Find some core that's small, but witnesses the property you want. And so when you're dealing with, again, large data problems, this is how you often have to think. That I can't compute it, but maybe I can do some compression and use the compressed object as my proxy. So this is probably the most important kind of large data manipulation you're going to see. In the next lecture, I will tell you about another kind that works primarily for geometric data, where you have two parameters, the size of the input and the dimensionality of the input. And that dimensionality can also be a big problem that you have to deal with. And we have the techniques for dealing with that. All right, see you Thursday.
So let's say the real life